project, electric microphone calibration was operated by Garrison Brown and Liang Dong from Mechanical Engineering Department of the Ohio State University. The objective of the project was to calibrate and analyze an electric microphone sensor and then make an application based on its function. Microphone is a sensor that converts sound waves to electrical energy. It's constructed with a diaphragm that vibrates when subjected to varying pressure from different sound waves. The experimental setup for the static calibration includes the microphone circuit, a speaker, and a mic deck, while the dynamic calibration setup has an extra SPR meter, also called a sound level meter. The microphone circuits utilize various resistors in series to minimize the voltage throughout to only 2 volts. The yellow wire in the circuit to the right aided in measuring the output voltage of the microphone. The SPR meter was used to measure the decibel level of different sounds while dynamically calibrating the microphone sensor. The lab view setup was also made as the picture shows to generate waveform from input signal and manipulate signals for data analysis. For the static calibration, the team set up the microphone to record the amplitude of constant decibel signals output from a speaker at set distances from the microphone. The distance was incremented by 1 inch from 0 to 12 and returned to 0. After experiments, the team got a plot showing the relationship between the sensor output voltage and the distance. A curve fit using MATLAB built-in function CF2 was used since the plot looks nonlinear. An approximate function between V and D was also estimated with the tool. With the parameters of the estimated function and the properties of the sensor from datasheet, the team evaluated the hysteresis error, quantization error, and the curve fit error using equations shown below. Then the total design uncertainty was calculated. It turned out that the uncertainty was not a constant and it varied with distance, so a plot was made to show the uncertainty. For the dynamic calibration, the team used a similar setup to the static calibration. However, this time the team recorded voltage of the microphone at frequency varies from 1000 Hz to 10,000 Hz, while making sure the decibel level read by the SPR meter remained constant and keeping the distance of the speaker from the microphone constant. The step of data analysis of dynamic calibration is shown here. Presented here is a plot obtained from dynamic experiments. The plot shows a relationship between the frequencies picked up by the microphone and the total decibel level at each frequency. Then the team made a curve fit. By calculating the decreasing slope of the curve, which is around 20 decibel per decade, the team ensured that the dynamic response was in first order, which with calculation the team got the time constant and bandwidth of the sensor. For the static experiments, the team found that the relationship between voltage measured by the microphone and distance is nonlinear, and the uncertainty of the microphone varies with distance. From the dynamic experiment, the team learned that the microphone is a first-order system and can be modeled as a first-order transfer function, and the useful frequency range of microphone is around 9000 Hz. Thus, the datasheet was made to collect all the data. After all the calibrations, we made a simple application like this.